So today, in today's class, we will talk about determinant and permanent. Okay, two very interesting problems. But before we get started, I want to, talk about one topic. It's so dynamic. So I want. So there are two ways of doing. When we don't know the amount of data that we have to handle, we use dynamic memory allocation, but there are some cases where we can get away without using dynamic memory allocation. Let's say in one of the problems, we worked with a vector, and usually the way we do is the way we define a vector is hash define max size, let's say whatever 50, and then we have main and then we say read vector A. So does this code makes sense? This is how we do, right? Read vector Sorry, it got disconnected. Today is not my day or our day. Key closer time. I think I lost some interesting conversation in the chat. Hey, where is it snowing? Why it's not snowing in Delhi? Same question, why it's not snowing in Hyderabad? Oh, okay. Thank you, Vinkesh. Okay. Okay. Okay, guys. Yeah. So where are we? So do you see here the code here, the code where the size of the array is fixed? Are you all with me here? So the problem here is if we have to handle data which is greater than 50, we cannot, this program doesn't work. And if the data is, the size of the data is less than 50, then there is a wastage of memory. When it is 50, it's not a big deal, but let's say if you have something like, 5,000 or 50,000, something like that, then what happens if the size of the data is less, then the data, then there is wastage of memory. Okay. So if you declare a large size, the summary is if you declare a array with large size, then and if the actual data is small, then there will be wastage of memory. And if the array size is small and if there is more data, we cannot work with the program. So this one way to handle this problem, there are many ways to handle this problem. So one way to handle this problem is by making use of heap memory. And when we use heap memory, there are two approaches to solve this problem. So dynamic memory allocation. So heap memory, dynamic memory allocation, dynamic arrays. The other is you use a totally, okay, sorry guys, 1 minute. The other approach is, I think it should be visible now. So I think the other approach is completely by making use of different data structures such as linked lists, trees, etc. So we will talk about heap memory, dynamic arrays, etc. next week. This week we use an alternate approach to solve this problem, which is called as variable length arrays. Variable length arrays. So in variable length arrays, the way we work is, so let's say intent, say printf, enter the size of array. All right. And then what we do is we have an array declaration here, int a of n. Okay, so now we read the vector a of n here. Okay, and then let's say you want to find the sum of elements in vector a of n. So we have this, we can have a function like this. See, using end of file is not the issue here. We want to know the size, that's a different problem. But here, what the important thing I want to see on line number 13 is the important thing that I would like you to see on line number 13 is the size of the array A is dependent on what the user enters on the keyboard. And also void. So earlier we were kind of passing array arguments like this. When we are trying to do something, let's say for some array function, we want to find some vector. Let me use the word vector uniformly. So this is the notation that we were using, and the fact that the array A and size are linked is in our mind. There is no, so this the way we do it is for int I is equal to 0, I less than size plus I, sum is equal to sum plus a of I, return sum int sum is equal to 0. So this all works, okay. So this works. Is this wrong? Anything wrong with this one? Okay, I will change the, anything wrong with this one? Apart here. So now, is there anything wrong in the sum function? We don't need line number 25. What is there? Oh, sum vector an. Okay. So there is nothing wrong in this function. Okay, the way we have written. So we have to write, yeah, size can go beyond all that. But the binding between the array parameter A and size is in our mind. It's not, the compiler doesn't know the binding between, we don't need bracket here when there is only one statement. The size of the size, no, if you give a wrong parameter for size, if you give the actual size of the array is 100, but if you give 1000, you can, this loop doesn't know, you just go ahead and write it. We need, I'm not writing code for read vector, okay. Control Shift I. So, are you all with me here? But if you want to make, focus on what we are doing guys right now, okay. So, but if you want to create an actual binding between the array, if you write it this way, then we are telling the compiler that some vector we are passing an array A and the size of the array is given as the first parameter. Are you with me here? This binding, and this will come really handy. This will come really handy when we are, and we no longer require this max size. So here on line number 3, we are telling the compiler that we are passing an array A as parameter, and the first parameter size, the size of that array, we are passing it as the first parameter. Okay. Are you all with me here? Array is filled with garbage. Okay. Are you all with me here? The line number 3, the earlier one, the alternate declaration that we made, sum vector int size. So this is an alternate way of defining this, okay? But when we define this, the compiler doesn't know that there is a binding between the size. That size is the size of the array A that we are passing as the first parameter. But on line number 4, we have an alternate declaration which kind of binds these two parameters in some interesting fashion. And this is not, so this sum vector int A of size, int size, this doesn't work. This is wrong. Okay. So now, why we are some of these things, they have a very important function in you can, if you use these things cleverly, writing programs for permanent determinant becomes easy. And also let's see dynamic matrix. Let's see. So this is the better way of doing it, line number 6, the way we are doing it on line number 6. So now we want to have focus on what I'm saying. So now you want to, let's say you want to work on a matrix. Okay. Earlier, what do? We kind of say int matrix A, something like max underscore size, and then we will have hash define max size 100, something like this we work. Okay. But this is not good, right? If you are working with a 3 by 3 matrix, why should we have a 100 by 100 matrix? Are you all with me here? So what should we do? So we say printf enter the square matrix dimension. Now, do you see how we can read a square matrix? A dynamic square, variable size square matrix. Now, if you want to have, let's say, you want to find int some matrix, we want to add all the elements of the matrix, then you can have something like int m, int n, int a, m, n. Okay. Or if you are working with rectangular matrices, you can have a declaration like this. Or if you are working with a square matrix, then you can just have. I hope this should work. Okay, and then we say for, let's say int I is equal to 0, I less than n, plus I, All right. Do you see the code? You're all with me here? GCC too few arguments. Okay. It's working now. It's compiling. Int main is okay. It's always int main. Return 0. Ah, is it? Are you all with me here on this code? The important thing here is we are passing, and it is possible for us to work on rectangular matrices also. Like for example, if you want, if you are working with rectangular matrices, you can just say int matrix M, int n, int A of M. Okay. Are you all with me here that how we can pass variable sized matrices to a function along with their dimension? Okay. So now keep this in mind. So what doesn't work, Gaurav? It works. This will perfectly work in 10. It's okay. What's the... No, we are not writing the complete function. Okay, so if you want it, this is int m int n, and I'm yeah, it works now. It's not complaining. See, this is the function signature now. Are you with me here? Are you all with me so far? Focus, guys. You keep getting distracted. Okay, so now let's come to the determinant problem. So the determinant problem, so we want to, let's say here, focus. We want to find the determinant of this matrix. This is a k by k matrix. The determinant of this matrix is the element A11 into the cofactor of A11. What is the cofactor of A11? That is, you remove this row in which A11 is present, you remove the column, and you have to compute the determinant of this submatrix. So this is what you have, term 1. So after that, what do? We go to element A12. So this is plus sign. Element A12 time, so we have to use minus A12 times the determinant of its cofactor. The determinant of cofactor for A12 is you remove the row in which it is present, you remove the column in which it is present, you get this whole matrix. It's a k minus 1 by k minus 1 matrix. This is a k minus 1 by k minus 1 matrix. You find its determinant. And then you go to A13, and A13 gets a positive sign, you find its cofactor and you compute its determinant, so on and so forth. Are you all with me here on this, the algorithm for determinant computation? This is the equation for computing the determinant. So now, why this is important? I will not write the entire code for determinant, but I'll give you some ideas on. I'll sketch that many of you have already written, but still, reviewing the ideas so that we will get a good clarity of thought is nice. So what do we do? So Control A, Control C. So we enter. Yeah, so we enter a square matrix, we read the matrix, we declare the matrix here, and then we have a function read matrix N A. Okay, so this is, and after we read the matrix, det_val is equal to compute determinant n comma a, something like int n. So is this how your main function looks like? You see, now you are working on general n by n matrices. You're not working on 3 by 3 matrix or 4 by 4 matrix. It's not like that. Okay, this is the first observation. So yeah, so don't ask why you are not reading read matrix, etc. I'm not going to write for you. You write it for them. We cannot return a matrix, Yesh. We cannot return a matrix. So int compute determinant. So what is the first parameter? We want to find the determinant of a n by n matrix. Okay. So what should we do? We have to iterate through the first row of A, right? Yes or no? We have to iterate through the first row of I. So we say for I is equal to 0, I less than n plus I. So we are iterating through the first row of I. So this is our matrix. So this is the value of I. It changes from I is equal to 0, 1, 2, so on and so forth. And the important thing is, and then, so remember, so determinant is a some kind of return det_val. So we would like to have det_val equal to, so let's say we have some sign. Yeah, good. You're all. So you have to do yes. So sign is equal to -1. So okay. So I have to figure this sign. I will keep this sign out for the time being. Determinant is equal to determinant val plus -1, or no, there is something there. We will do something. But what is important here is we would like to extract cofactor. We want to extract cofactor. Okay, power is a very bad thing to do. So we want to extract cofactor of which element we want to extract cofactor? What is the element for which we should extract cofactor? We'll think about sign later, don't worry. Okay, what is the A of 0, 0, I. Okay, so but what we should give is, we need to give, it's all the time, it's the, we want to write a extract cofactor function, and we say it's always row 0. So in row 0, what is the element I? So that's what we want to pass. Okay. And we give A as parameter, and we would like to get the cofactor in B. And what should be what is the dimensions of the matrix B? What is the dimension of the matrix B? Int B n-1, n-1. So the dimensions of the matrix B is n-1 by n-1. So we extract the cofactor from of the ith element from matrix A and store it in matrix B. Okay, and then that's it. So here we say compute determinant of B, and what is the dimension? n-1. Does this make sense? No? Sign is okay, guys. Okay. I want you to focus on, yeah, okay, we'll fix, we'll fix the sign. So otherwise, let's say I'm changing the problem slightly, you know. So I don't care about the sign, I just want positive things. So, so maybe in order to get the sign right, int sign is equal to -1, and we say sign is equal to sign times -1. And okay, is this okay? Does this work? When we enter, this doesn't work, huh? It works now. Initially the sign is equal to 1. When you come back, it is -1. Again, it becomes 1. It keeps flipping. It works. So in this whole thing, what is it that you have to write? You just have to write the extract cofactor function. Does this make sense? Extracting cofactor. Okay, we have to multiply it with A of yeah, sign times A of 0 I times star. Okay, base case. So what is the base case? If n equal to, it can be n equal to 1 or 2. If n is equal to 1, then return A of 0, 0. Are you with me here on this problem? How? That's all, no? Did you see how we are using the recursion here? Okay, so yeah, n is equal to faster. I'm not trying to optimize. I want to do the dumbest way possible, okay? Because In the sense, just trying to get it right. Okay. Do you think you can write no function on line 15, extract cofactor function? Can you write? You just have to copy some elements of row A of matrix A to some elements of B. That's all. Okay, are you all with me here? Yes, no, maybe. Happy with line number 15? Don't copy paste code here. Okay, good. Here we are using recursion nicely. The reason I want you know, some of you are talking about you're all oh, yeah, so yeah, extract cofactor, it may require some more parameters. Yeah, it require n as a parameter. Yes. Okay, someone. Okay, so what is the question? Yeah, the question is, some of you were mentioning earlier about using global variables and blah. My point here is by using this dynamic memory on line number 7, variable length array on line number 7, we are able to handle this recursion easily. Otherwise, it would be difficult. Yes or no? If you don't have line number 7 variable length array, recursion would have been difficult. Line number 7, so that is the key here. That's the reason I introduced this whole variable length array topic here, because that makes the whole problem much more easier to handle. It's not a dynamic array, variable length array. The array on line number 7, its size, it's dependent on the parameter n that is being passed. Wastage of memory, actually, even I'm fine with wastage of memory. But in terms of simplicity of writing the code, don't you think this is a simple way of writing code? Because that is how you even think mathematically, right? So if you see here, let's see clear all my drawings. So mathematically speaking, let me do one thing. I'll go here. So if you see the loop, no? So this is what we are doing exactly. This loop we are extracting A11, what you have here, this summation, this loop, okay, this loop or this summation. So we compute the determinant of the cofactor. A11 into determinant of, in first iteration, we compute the determinant. We extract the cofactor, compute its determinant, you multiply, you accumulate. In the second iteration, you extract the cofactor. No, you compute its determinant, you do whatever it is. So here, between here to here, there is a mapping, clear mapping. And we are using recursion to do it very nicely. And variable length arrays are coming in handy. So I want you to think if you may have alternate clear better ways of doing it. I don't deny, but I want to see at least a basic baseline version of this code. I would like you to understand. See, you can declare n, but the problem is when you are recursing, this b, the problem I want you to understand is, let's see, where should I draw this? Let me draw here itself. So the matrix A is there. In order to compute the matrix A, we want to compute the determinant of a k minus 1 times k minus 1 matrix. Okay, how do you compute the determinant of this? So you recurse, no? So what happens is, so from in order to let's do one thing. Let me. So here, so here you want to find cofactor, the determinant of cofactor of C11. I'm using math. Let's use C01 so that it becomes easy. And then you want to work with C0. So C01, C00, C01, C02, so on and so forth. You keep going. So here you extract the cofactor of this and store it in B and work with B and you recurse. This is recurse. And then after you come out, you extract this cofactor and store it in B and then again you recurse. Are you seeing what is happening here? I don't know the cofactor or minor. I'm thinking, no. But when I say cofactor, I mean this is the cofactor. Are you with me here? This recursion, how recursion is happening? And when you go look into this tree, it is like a fresh look. It's like zoom in. It's like, here you are just working with an n-1 by n-1 matrix. You want to compute the determinant of an n-1 by n-1 matrix. You repeat the same process. So, but what happens is, one question I have, what is the memory that is being consumed? Yeah. What is the memory? So the matrix B is different in all the activations. What is the memory? What is the original size of the memory? This is a question that I want you to work on. So you start with an n by n matrix and then you go to an n by n-1 by n-1 matrix. You keep going down until a 1 by 1 matrix. It's not n factorial square. Yeah. It is approximately n cube. Yeah, that's true. So why is it approximately? Yeah, so Tejas got it. So yeah, think about it approximately. I want you to solve this, think about this carefully and solve this one. Solve the, analyze this code. Analyze this code. Okay. So far, so good. Do you understand the algorithm and can you try to analyze the space complexity of the algorithm? Can you analyze the space complexity, time complexity of this algorithm? Okay, good. I want everyone to solve this problem. Those of you who didn't get it, no, so far, can you go ahead and do it? No, you will get the time, but you should not take, after with all this discussion, you should be able to do it today. Can you do it today? I want you guys to finish the determinant problem today. Okay, those of you who finished with all this discussion, you should understand it and try to solve it today itself. So now let's go to the next problem, which is on permanent. How many of you understood the permanent function itself? So in permanent, what we do is you take all permutations. Okay, like for example, so like for example here, you can see so let's say what are all the permutations of 1, 2, 3, 1, 2, 3, 1, 3, 2, 2, maybe 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay. Same as determinant without sign, huh? Is it? Okay. Then both are the same complexity. Okay. I am not sure. That's not true. So permanent of a matrix, I know that can you give me a link where in 2 by 2 it may work, but it's not true in general. No, it's not like that. It's not. Is it? Then it's wrong then. No, not if you change the definition of permanent, then then that's a different story. But permanent, it's not. Hey, listen. Okay, just take a step back and listen. Okay. No, that's not the sign, guys. That's not the sign. It's no. Because the definition, see what happens is did you study permutations in discrete math course? Abstract algebra, did you study a bit of abstract algebra? See, listen to me. It so turns out permanent, the definition of determinant. Yeah, listen to me, listen to me. Maybe I might be wrong, but I would like you to consider this. Okay, I might be wrong. IIT Kanpur says, huh? That's how you read IIT, what IIT Kanpur said. Okay. So -1 to the sign of permutation. Yes, listen, that's what I'm trying to tell you. So every permutation we can, there is a function associated with a permutation which tells whether the number of transpositions in the permutation is odd or even. Okay. So what happens is, listen guys, it's English language. You are prone for, so if you have this sign, when they say drop the sign here and you get the permanent. What happens is when this sign is there, whatever the Kramer's rule that you have figured out, that function and this function turns out to be the same. But if you drop this sign, you don't get the permanent function. The complexity of, so permanent is way more higher. The magic, just dropping this minus sign will make permanent function extremely hard to compute. But so what you are, so here, whatever that we have seen, A11 into determinant of k by k, A1 in A12 into determinant of whatever the cofactor. This is a very deep complexity theory problem. So these two are equivalent. But when you drop this, then what happens is it's not the case that you just make this one plus and you get everything. Are you trying to, am I making sense? Okay. Let me do one thing. Okay, so you see, when you say drop the sign doesn't mean make that minus into plus. There is a signature of every permutation. There is a sign function associated with a permutation. So in determinant, this sign function will be there. In permanent, this sign function is not there. So computing permanent is extremely hard in terms of the time taken versus this. So here, whatever the thing that we did, Kramer's rule, etc. for that, it will work this, and it becomes an easy problem to solve. But this one, it's not like you just, the sign is the number of transpositions that are there in a permutation. So that's the reason I asked whether you studied abstract algebra and permutations, not the permutations. Or you does, whether we solve this problem now or not different, but I want you to understand this, but the determinant and permanent are not the same. Some function, it's like, like if the permutation is 1, 2, 3, and 1, 2, 3 gets mapped to 2, 1, 3, then we write it as 2, 1, 3, 3, then the number of transpositions is 1 or something like that. I have to look into the definition. What is A sigma I? That is, that's what I'm trying to explain. Before I'm trying to explain, you said, hey, determinant is a solved problem. You just remove the sign and it's all done. So solving permanent is a way harder problem than determinant. I think even your TS got it wrong. Arey, listen, take a step back. Let me stop recording this story. Okay. No,